I can't say how honored and grateful I am for these incredible awards and for your support for our research. Thank you so much. And Andreas, I really appreciate you calling out humor, and I think it's very important. And I think somehow, like, right next to humor is also hope. And I think, though that's not an explicit title of this talk, I think you'll see that it's part of the theme. And so the title of the talk is From Shields to Plowshares, Understanding and Anticipating East African Extremes. And the shield in this talk is the shield that we've managed to erect to keep more than 100 million people from starvation every year. And the plowshare is the aspiration that we can use the same climate science that we use for famine early warning to improve agricultural outcomes for farmers in Africa, many of which are women. We're going to give some background to talk about how the Climate Hazards Center helps shield millions from extreme hunger. We're going to talk briefly about how the Climate Hazards Center and KIT Science is helping right now. And that describes our analysis of the extreme 2019 short rains. So these are the October, November, December rains in East Africa. And then I'm going to describe how that science was applied in 2023 to anticipate extreme rains in East Africa and fuel advisories that went out to millions of people in Kenya, helping to improve their agricultural productivity. Then we'll get to a lot of the important future work that we're hoping to do in collaboration with the Karlsruhe Institute. Basically, the Climate Hazards Center was started in 2003 at the University of California, Santa Barbara, to help put more climate in famine early warning. In the 1980s, more than 1 million people died of famine in Ethiopia. It was one of the greatest humanitarian crises ever. And then following that, the US government put together this famine early warning systems network. I got involved with it while I was still in graduate school to help use satellites and climate models to anticipate droughts and improve food security interactions. And also, our center supports regional scientists in Eastern, Western, and Southern Africa. So these are full-time scientists on the ground that give us a tremendous ability to engage with the institutions in these countries and help build up their ability to deal with climate extremes. So we've been doing this for a long time, and it's really tremendous. And as part of that work, in collaboration with many partners in Europe, China, all across the world, this community of practice is now providing a shield against increasing food insecurity. So, this is kind of a complicated graphic, but these circles denote the number of very hungry people who, if they don't get humanitarian assistance, are likely to starve. And this number of people requiring this assistance has increased from about 70 million in 2017 to about 129 million in 2023. This is a huge crisis, and it is very troubling. However, this is the hope. We are, to a large extent, keeping a lot of people from dying of starvation, and that's a really great thing. But one of the things that we're trying to do, and that we'll talk about today, is how we can use climate resources developed to combat famine and try to use them to help farmers become more successful and battle climate extremes for themselves. This is a snapshot of the members of the Climate Hazards Center. On the left, we see a lot of the people who work in Santa Barbara. These are climate scientists, remote sensing scientists, computer programmers. And on the right, we have our international team of regional scientists who are in East Africa, West Africa, Southern Africa, Central America, Central Southwest Asia. And together, we are a team of what I call humanitarian earth scientists. And that means that we're earth scientists who are focused on achieving humanitarian goals. And that actually requires often a lot of innovation and the highest quality science because what you're doing is so important. Of course, there's Andreas Funk, who you probably have met before. And both Andreas and I work closely with professors Sharon Nicholson, who's been a real mentor of mine for many years. And in this project, we will be working with an excellent young climate scientist out of Nairobi, Madeline Gudashova, who is the lead forecaster for that region. And go on to the important question is how can the Climate Hazards Center and KIT Science help East Africa cope with climate extremes and climate change? And we're going to look at a pretty focused example based on a paper that we collaborated on that looked at the extreme rains in October and November in East Africa in 2019. So one of the ways that we're collaborating is by supporting the development of excellent rainfall data sets. And yes, version 3 of the TRIPS is coming out soon, Andreas, and you contributed a lot to that. And so if you can't see extremes, you can't study extremes, and you can't develop systems for predicting extremes. So here we're looking at maps of rainfall in October, in November, expressed as percentages for anomalies from the long-term mean. And so these deep blue areas are 200, 300, or even 400 times the normal rainfall. And this is extreme rains that were associated with catastrophic flooding. So Andreas and Sharon and I studied these rains, and we worked on analyzing the predictable drivers of seasonal extremes in East Africa. This is one of the ways our science can help. And we linked these extreme rains to an extreme value, what's called the Indian Ocean dipole. And this dipole is very positive when you have exceptionally warm sea surface temperatures in the Western Indian Ocean. So when that gets really warm and climate change is increasing the frequency of this happening, you tend to have flooding and catastrophic rains over Eastern East Africa. And then the group here contributed this really fascinating analysis of this extreme kind of atmospheric Kelvin wave. So I'm good at seasonal climate prediction. The group here is really good at looking at tropical meteorology. And this is kind of a complicated graphic. I'm not sure I even understand it, to be honest, but you can ask Andreas later. But basically what it's showing is that in East Africa, between November 22nd and November 25th, this very intense storm swept through and created catastrophic flooding. And this is one of the things that we're going to study next year to try to understand and predict. And so another way that we can help is by working with African partners to improve early warning and anticipatory action systems. In 2019, there was catastrophic flooding that was not well anticipated. In 2026, we hope that our partners in East Africa can better anticipate these extremes and respond. And the fourth thing that we're doing is we're working together to develop thermodynamic analyses of the driver of extremes. And I'm kind of chuckling because I realize that that's a big word, thermodynamic. But basically it means heating up the atmosphere to make it do stuff and cause extreme weather. So basically, as the oceans warm in the Indian and Pacific, right, the atmosphere in the lower part of the atmosphere, what we call the troposphere, is hotter, and it has more water vapor in it. And that basically causes things to become more dynamic. So extreme precipitation events are becoming more extreme, and these are giving us opportunities for prediction. And so we can think about this thing called the Walker circulation. Named after Sir Gilbert Walker, one of my heroes, who was studying the famines that happened in India in the 1920s. And he's sort of the father of modern climatology. And this idea of trying to prevent famine has been with us since the very beginning. And so East Africa, this region right here, is dry on average because of all this rain that happens over Indonesia is associated with dry sinking air over the Eastern Horn. So under typical conditions, Somalia, Kenya are dry. And sometimes when we have the right sea surface temperature conditions, this can amplify and you can get more severe droughts. But this whole thing can cycle the other way and you can also get flooding. And that's what we're seeing in this region, is a sequence of extreme rains or a sequence of really dry seasons that we're getting really good at forecasting. We're now going to transition from the paper that we did to a real-world application that used those research results. In the summer of 2023, in July, our group at Santa Barbara put out a blog that predicted these Western Indian Ocean sea surface temperatures in September, October, November, December, and said, oh my gosh, these look like they're going to be super hot, just like we saw in 2019, the study that we did with KIT. And we started putting out alerts and started working with the Kenya Meteorological Department to say that we think that this map is a change in the start of season. And so in August, we were putting out studies that said, hey, we think the season is going to start earlier. And hey, we think that the water availability for crops during this season is going to be way above normal. So if you're a poor farmer in Kenya that's going to plant this season, this might be a good time to double down. Maybe you want to buy some fertilizer, or you might want to buy some good hybrid seed, or maybe you want to spend more time cleaning your field and doing land preparation because you have a really good chance of being successful. And we also worked with this really neat group called Shamba Shepa, which is a company in Kenya that puts out videos and SMS messages and television shows that tell farmers how they can increase their crop production. And so this video basically said, hey, we think that there's going to be a ton of rain this October, November, December, so you might want to build a water retention pit and store that water. And so these are this is a direct connection between research that we did with KIT and real world applications that we did with the Kenya Meteorological Department that increased resilience. 1 year later, so basically from July of this year, essentially the situation flipped. And I won't go into the details, but instead of looking like it was going to be above normal, the sea surface temperature forecasts looked like there was a really good chance of below normal rains. So I got on a plane, I flew to Nairobi, I met with our partners at the IGAD Climate Prediction and Application Center, and we agreed that we wanted to work together with partners to put out a multi-agency alert. If you take dry seasons in the Horn of Africa and look at this atmospheric heating, what this plot on the top shows is that when you get more rainfall and associated atmospheric heating in this area around Indonesia and less heating in this area over the Western Indian Ocean, you tend to get really predictable dry rainy seasons. And by our assessment, we thought that October, November, December of this year was going to be down here, where you had a really big frequency of below normal rains that are shown with those red dots. So we felt like we had a lot of confidence to put out an alert. So we worked with our East African partners. We worked with the World Meteorological Organization. We worked with a ton of different people to put out an alert that had about 14 different logos on it. And it just said that preparedness planning is needed for potential drought in the Eastern Horn of Africa during the October, November, December rainy season. For me, this was a huge achievement. So Andreas talked about the famine that happened in 2011 in Somalia. And then he talked about the drought that happened again in 2022. And between those 2 years, our science had advanced a lot, but we had never done this. We had never, in the summer, 5 years before the rainy season ended, put out a joint alert that is led by the Africans warning of potential drought. This is our current assessment of the drought based on our satellite observations and some weather forecasts showing the percent of average precipitation. And so basically, in all of these red areas in Somalia, there's basically gotten no rain in their rainy season. And so they're now looking like they're in really bad shape. But the good news is that there was advance warning and people were expecting this. So humanitarian responses are being made available. We can then look further out to March, April, May of next year. And this is, again, some more work that we've done together with KIT. And if we look at the sea surface temperature forecasts for March, April, May of next year, so we have this amazing ability to look out into the future many months and to get a good sense of what the sea surface temperatures look like. So these are standardized anomalies, and basically these dark red places are probably warmer than they've ever been in the past. Climate change interacting with natural variability is just making this insane, or in the forecast is expected to be insanely hot, while we have below normal sea surface temperatures in the Eastern Pacific. And this is a pattern associated with drought. And so there's a good chance of 2 droughts in a row in Somalia, which sets the stage for potential famine. And if we plot those, we get this scatter plot where basically we can look at these, what I call Western V sea surface temperatures in this yellow box, and these East Pacific Nino 3-4 sea surface temperatures shown here on the y-axis. And I realize this is kind of a technical figure, but I decided to show it because this is a world with climate change that we're living in. Basically, what this is suggesting is that these Western V sea surface temperatures, right, this area here, is expected to be far warmer than it's ever been in the past. And our science has suggested that when that's the case, that you're likely to get below normal rains in Eastern East Africa. So the food security community is already assuming that the rains are going to be below normal in March, April, May, and developing responses under that assumption. Will it happen or not? I don't know. It's a little hard. We've never been in this world before with climate change, but we are developing the tools to expect these extremes. So I think I'm just going to skip forward because I want to have plenty of time to talk about our description of our CHC KIT science plan. So we've seen, I think, a lot of successful advances on seasonal climate prediction. What we don't have is similar advances at subseasonal timescales. And that's what we're going to try to work on. So one of the things that's missing is an adequate understanding of the drivers of extreme East Africa rainfall events at subseasonal timescales. So I think one of the great success stories that I described just a few minutes ago was how our collaboration with KIT helped us know that the 2023 October, November, December rainy season was going to be extremely wet. But still, widespread flooding was poorly dealt with. Every climate scientist thought that the rains were going to be heavy in 2023, but societal preparedness for flooding was minimal. And so we need to address that. Another thing that's missing is ways to incorporate the influence of warming air temperatures into subseasonal precipitation forecasts. So this middle panel shows standardized anomalies of maximum temperatures from November 6th to the 10th. And it's just basically all those areas that are orange and red are exceptionally warm. But what we need to try to work through, and this is one of the things we're going to do in this project, is the potential contribution that warming may have to driving more extreme precipitation events. So we have a hypothesis. In a warming world in which warming air contains more heat, energy, and moisture, atmospheric wave disturbances are becoming more intense. And you could just replace atmospheric wave disturbances with storms, and then other regular people might understand you. So if we think about a line that goes from left to right with time increasing, right? We know that there are these atmospheric waves that bring rain, right? And our hypothesis is that with climate change, warming the atmosphere, increasing the amount of water in the atmosphere, those are more intense. And those more intense fluctuations cause floods, but there are also opportunities for forecasts. Our second hypothesis is that in a warming world, forecasts of wave-enhancing conditions can help increase subseasonal forecast skill and societal preparation. So wave enhancing doesn't mean that you're wearing long gloves, right? It means that the atmosphere has more energy in it, that the atmosphere has more water in it, so that when you get an atmospheric wave pattern, a storm, it's more intense and dangerous. So we can look at things like long forecasts of the amount of water vapor in the atmosphere, or the instability of the atmosphere, or maybe the vertical motion in the atmosphere, and try to use those to produce improved forecasts. We can look for improved extreme weather predictors, atmospheric heating, the total precipitable water in a column of air, the instability of the air, perhaps wind shear, and integrate those into better forecasts. The group here is excellent at looking at wave patterns. And so we're going to look for improved wave pattern predictors based on frequency domain analyses. And then we're going to try to take those potential predictors and combine them into artificial intelligence-based extreme rainfall forecast methods, which can be used by groups in East Africa to make hydrological localized alert systems at the IGAD Climate Prediction and Application Center, the Kenya Meteorological Department, and the Somalia Meteorological Department. That's the long-term vision. It's not all going to happen in 6 months, but I think that in 5 years, this will happen. And the support that you're providing will help us get there. Thanks.